Hey everyone, welcome to my first video. This video I will be reviewing mathematical induction, which I believe is topic 1.3 in the IB Mathematics HL curriculum. So I'll be starting off with an easier problem and then working my way through harder ones so that you get a feel for all the different kinds. And yeah, so I got this problem from the Oxford IB Diploma Program Mathematics HL book. I'll put a link to it in the description below the video. But yeah, so this is the book I got with the course. It's probably what you'll get to if you're in IB Math HL. So yeah, so let's start off. So if you don't know already, so the first step is to understand the question first of all. So use mathematical induction to prove that n squared is greater than 7n plus 1 for all n is greater than or equal to 8. I believe the question should say for all n of elements of integers or something like that. Usually questions will say that just so you know what kind of answer you should be getting and how to manipulate the problem. But it usually doesn't matter too much. So it's fine. Okay, so step one. The first step is always to prove the equation true for what they give you, just as a fundamental basis to prove that it works at the fundamental level. Now let's take it up a notch. So step number one is to prove true for n equals 8, because we need to prove it true. That's all we're doing. So we need to take a look at the left-hand side of the equation that they give us, which is the n, and then the right-hand side, n squared, and the right-hand side, just 7n plus 1. Just left-hand side of the equation, and right-hand side of the equation. Simple as that. So for the left-hand side, we have 8 squared, because we're just plugging in 8 for n, which is 64. For the right-hand side, we plug in 8 also. 7 times 8 plus 1, 57. We know 64 is greater than 57. In other words, left-hand side is greater than right-hand side. Therefore, true for n equals 8. Easy as that. First step done. Second step is the easiest step. 1 and 2 are very easy. 3 is the only hard one. And we have to just say, assume true for n equals k. So all we're doing is plugging in k for all values of n, just to set the basis for step 3, which is moving up a level with k plus 1. And this assuming true for n equals k, it's just a stepping stone for the next step. That's all it is. No, nothing else. So we just have to plug in k. So k squared is greater than 7k plus 1. And you'll see why this step is important in a couple seconds, honestly, when we move on to step 3, which is for n equals k plus 1. Now we're plugging in n equals k plus 1. So we're taking the same thing. Let's split it up into left-hand side just to make it easier, and right-hand side. So k plus 1 squared, right? And then right-hand side equals, well, it was 7k plus 1 plus 1, which equals 7k plus 8. And this equals k squared plus 2k plus 1. Okay, awesome. So now we have to look back at step number 2. Step number 2 says what? Step number 2 says that k squared is greater than 7k plus 1. This is the part of mathematical induction that is difficult, or for me at least, because it's not easy for me to look at these equations and just mess with them to get my answer. But it's an acquired skill that you get just from practicing. So you can see that it says k squared is greater than 7k plus 1. We have a k squared here. So let's try it out. Let's see if plugging in 7k plus 1 for k squared gets us anywhere. So because it's greater than, it's not going to be, we're not going to say equal to on the next step. We have to say greater than, because it's not equal to, it's greater than. So we plug in 7k plus 1 for our k squared on our left-hand side. So we have 7k plus 1 plus 2k plus 1. Because all we did was plug in this for that. That's my attempt at a squiggly bracket. Okay, so now what did we say our k equals? Our k is n. But what did we say our n equals? Our n works for n equals 8. So to make our life a little bit easier and to prove, we're just going to plug in 8 for k. So it's greater than 7k plus 18, because 2 times 8 is 16, plus 1, 18. But wait a second, isn't our right-hand side 7k plus 8? If our right-hand side is 7k plus 8, and our left-hand side is greater than 7k plus 18, we know left-hand side has got to be greater than right-hand side. So that is greater than 7k plus 8. Just for obvious reasons, 7k plus 8 is greater than 7k plus 18. It's less than 7k plus 18, sorry, which is greater than right-hand side, which is, as we just said, 7k plus 8. Therefore, true for n equals k plus 1. We did it because, remember, what are we trying to prove true? We're trying to prove that n squared is greater than 7n plus 1 for all values of n is greater than or equal to 8. So we just proved it true for n equals k, then we proved it true for n equals k plus 1. So the way my teacher has described it is, now that we've completed it, we have to tell the story of what we did and why we proved true, what we proved true, and how we did it. So we want to say, as we proved it true for n equals 8, and if we assume true for n equals k, then n equals k plus 1 is proved true. Therefore, true for all n is greater than or equal to 8 by proof of mathematical induction. Now, this story can vary, and you can do different versions of this story, and it depends on what your teacher wants you to see. But if you say something like this may also not be perfect. I kind of just did this off the cuff, but as long as you say something, use the word assume. Assume is very important, and just tell your story of what you did. It's not very complicated. You just don't want to lose easy points on this, because you will if your teacher is a little strict on this. So for our next example, this is another example from the Oxford book. We have a sigma one. Now, these are very, very common, and I can almost guarantee you, I can guarantee you are going to run into these on your test, on your homework problems. You're going to encounter these a lot, because these are very common for mathematical induction, right? Okay, so same steps though as before, just a little bit different process and maneuvers once we get to the end. But you'll see, and again, it's all just playing around with it till you get to the right spot, because you're going to have really hard ones. These are relatively easy, but you're probably going to end up running into really hard ones on your test. And I'll actually go over one of those really hard ones in this video, but you're going to just have to play around with it and try to get to that k plus 1 of the k in step 2. All right, and you'll this one is if you don't get what I just said with the k plus 1 stuff, you'll understand after this example. All right, so let's go into step number 1. Step number 1, prove true. So we have to prove it true. Let's prove true for, what could we do? We could do n equals 1. N equals 1 is a great way to just prove true. Standard. This equation works. Another reason to do it is because this sigma starts at r equals 1. So just plug in r equals 1 just to prove, hey, look, our thing works. All right, so for left-hand side, we have 1 times 2 times 1 plus 6, which is 8. Right-hand side, we have 2 over 3 times 1 times 2 times 6, which equals 2 over 3 times 2 over 1 times 6 over 1. These go to 2, and we have 8. So look at these, left-hand side equals right-hand side. Therefore, true for r equals 1. Awesome. Step number 1 done. Step number 1, easy as cake. All right, 2. Just plug in k for all n. Oh, wait. Okay, so r equals 1, n equals 1. You still have to plug in both. Yeah, you still have to plug in both. I didn't see these are different. I don't think it really matters. We'll see later, won't we? When we try to get the answer. All right, so true for r equals 1, or you could say n equals 1. Same thing. I don't think it matters. We might lose points. I don't really care. What matters is we know it. Okay, so 2. Assume true for n equals k plus k. I said k plus 1. So true, assume true for n equals k. Oh, shoot, I didn't say n equals 1. Okay. Cool. I'm just going to make that in. All right. Assume true for n equals k. Just plugging in. Okay, so now assume true for n equals k. We're basically doing this. We're plugging in k for values of the sum that we have on the left-hand side. So let me show you what I mean. So on the left-hand side, we have, for r equals 1, let's say, we have 1 times 8. For r equals 2, because, it goes up incrementally up until n. It goes up incrementally up until n. Oh, yeah, so quickly backtracking for a sec, sorry to confuse you. But before, we plugged in values for n equals 1 because it goes up. The sigma ends at n. And that's why over here, there's an n, and over here, there's an r. You're just plugging in for r until you reach n. So you do want to write prove true for n equals 1, and you do want to say true for n equals 1. So not r. Sorry for that confusion, my bad. Okay, so then plugging in for 2, we have plus 2 times, that would be 2 times 2 plus 6, which is 10. And then plus 3 times, that would be 12, right? It's 2 times 3 plus 6, yep. And then so plus, and you can keep going on and on and on until you get to n, right? You can keep going until you get to n. We don't know what n is. N could be 900 for all we know. So that goes up until n, and we want to plug in k for all values of n. So k times k, 2k plus 6. Okay, all good. And then now we want to make that equal to 2 over 3 k plus 1, k plus 5. All right, that's all we have to do for step number 2. Step number 2 is done. We're almost done. Well, not really, actually, but step number 3 is always a killer. Always. Just practice. Okay, so for step number 3, now we want to do the same thing, except for remember, all values of k are now k plus 1. So prove true for n equals k plus 1. All right, same thing. 1 times 8 plus 2 times 10 plus 3 times 12 plus up until k, 2k plus 6. Now you're probably thinking, but you're probably thinking to yourself, but you just said plug in all values of k plus 1 where k was. yes, that's what we're doing. But remember, in this sequential order, we're going up until k, as we just did in step 2, but now we want to go one value further to k plus 1, right? We're trying to find k. That was the point of step number 2. Now we're going to k plus 1. So go one more digit higher, and we have k plus 1, and then 2k plus 7. Okay, so now you're thinking, what the heck do we do with this? There's nothing to do. Actually, there is, because look at this. Look how useful step number 2 is. Step number 2 is always so useful, and always look to substitute step 2 into step 3, because that's how you're going to get your answer. In step number 2, we have all of this is equal to this. Well, look at what we have in step number 3. We have all of this again, just plus one more value. So what can we do with that? You can plug this 2 over 3 k, k plus 1, k plus 5, and then now bring this down, plus k plus 1, 2k plus 7. Now we can solve this mathematical induction proof. So what we want to do from here is we see, all right, let's see if we can pull anything out. Well, I see a k plus 1 that's common with both parts of this addition equation, kind of, not really equation, but thing. I don't know, I'm lacking the term. So, but we could take out a k plus 1, and then what do we have left? We have a 2 over 3 k, k plus 5, plus 2k plus 7. 2k plus 7. I think it's 2k plus 8. It's 2k plus 8. It's not 2k plus 7. My apologies. I messed that up it's 2k plus 8. Because what you're doing is you have 2 times k plus 1 plus 2, which is 2k plus 8. Mistakes are super easy to make. It's just got to be careful. I've made so many mistakes already. All right, that's what we have here. Now, what else can we do? We can multiply in. So what do we have? We have, if we multiply everything within those brackets we made, we get k plus 1, 2/3 k squared, plus 10 over 3k, plus 2k, plus 8. That's just by multiplying these together, and then this to that. That's all you're doing, just multiplying those. And then you have, for this, you have, oops. Now you can take out a 3 to make this easier to add into, because let's be honest, who wants to add 10 over 3k plus 2k? I mean, we could, but let's just make it 10 times easier for ourselves, because like we're on a time test, you don't want to waste your time with that nonsense, and you want to make it easier for yourself in the future, because it won't be easy for you if you do that. So if you multiply them all by 3, right, you're getting rid of that denominator 3. So you'll then have k plus 1 over 3, 2k squared, plus 10k, plus 6k, plus 24, right? You're multiplying by 3 to get rid of those two denominators. But then you have to remember to multiply that 2 by 3 and that 8 by 3. If you forget that, you're not getting the answer, and you're going to be stuck. All right, so now we can just make this, to make it easier for ourselves, plus 8k. Let's move this closer. Okay. Now, oh wait, 10 plus 6k. Am I stupid? My bad. 10 plus 6k is 16k. Again, mistakes. Just I'm thinking 2 steps ahead, but I have to take it slow. All right, so now we have this. Now this is where the 8k comes in by just taking out a 2. take out a 2, and you have k plus 1 over 3, because multiply in a 2, and now we're dividing out a 2. So now we have k squared plus 8k plus 12. That's where I was thinking of the 8 from. Okay. Now the rest is pretty, now that we know what we're doing, we can see this is very similar to this. We just have a couple more steps and we're home free. If we factor this, we get k plus 2, k plus 6, because, well, what multiplies to 12 and adds to 8, 6 and 2. So k plus 2 and k plus 6. And then we have 2k plus 1 over 3. Look at that. Okay, so we're very close. All right. So to get to our goal, it's important to remember your goal. Your goal is to get to this, but you're trying to get to this, but in k plus 1 version. So let me just make that clear. What you're trying to get to is k plus 1 for all k's in this equation. I know that probably doesn't make any sense, but here, 2 over 3, k plus 1, k plus 1 plus 1, and then k plus 1 plus 5. That's what you're trying to get to. K plus 1 for all values of k. Because that's how you're proving. You're saying, look here, this always works, because when you plug in k and then you solve using the things that we've proven true already, that the next step is the k plus 1, it's all true. That's the whole point of this proof. That's what we're trying to get to. So your goal is to get to your step 2, but k plus 1 version. All right, now that we got that out of the way, we can see, so we're trying to get to what we just set up there. So if we make that, oh, also, it's also good to put equals next to everything you're doing, just on your way down, just to show, that you're incrementally moving along the process. So we have 2 over 3 times k plus 1, right? Because that's what the 2 times k plus 1 over 3 is basically equal to, 2 over 3 times k plus 1. Then times, what is k plus 2 really? K plus 2 is a hiding k plus 1 plus 1. K plus 1 plus 1. And then what's k plus 5? K plus 6? That is a hiding k plus 5 plus 1. K plus 5 plus 1. And this is equal to your right-hand side up here. So you can say, therefore true for n equals k plus 1. And then you'll write your story, right? I did that before. It takes a little bit of time, and I don't want to make this video too long, but it's simple. As we proved true for n equals 1, and then we assumed true for n equals k, then we proved true for n equals k plus 1, and therefore this is equal to this. That's all you got to do by proof of mathematical induction. All right, next problem. Okay, so now this problem is a little bit more difficult. I actually had this problem on my practice test for this test. That's where I found it. So this one is going to be useful, really useful. So yeah, so as you can see, I started typing it, but then I realized I can't type all this stuff. So let's read it. So use mathematical induction to prove that for all n of elements of positive integers, that 2 to the 4n plus 3 to the 3n plus 1 is divisible by 11. So now we see this, and basically that's just to tell us n is an element of an integer, of all integers that are greater than 0. Positive integers, simple. That's not too difficult. Z stands for integers. Never mind that. Okay, so let's go on to step number 1, and I changed my pen to red to separate it from the question. Okay, so we want to just prove it true for n equals 1. So for n equals 1, we have for both sides of the equation. Oh, not both sides. Now it's not an equation anymore. So yeah, 2 to the 4 times 1 plus 3 plus 3 to the 3 times 1 plus 1. Now, what is this? This is 2 to the 7 plus 3 to the 4. And that, I believe, is 209. I'll plug that into a calculator real quick. Yep, 209. So 209 is 209 divided by 11, because that's all we're trying to prove. That's divisible by 11. Yes, 209 divided by 11 is 19. Therefore, put a check mark if you want. Therefore, true for n equals 1. Step number 1, complete. Step number 2. Step number 2 is assume true for n equals k. It's important to write assume in both the story at the end and when you're writing at your step, because you're trying to show that at this point in the proof, we are guessing and assuming that n equals k, so that later when we show that, well, not even guessing, because we're just making n equal to k, but we are then later in step 3 using that answer to get to the right answer. You know what I mean? You know what I mean? We're good. All right. So just plug in k. So the original question is 4n plus 3. So 2, 4k plus 3 plus 3, 3k plus 1. And now this is where you want to add a little bit of your own little spice, if you will. So we want to prove that this is divisible by 11, correct? So why don't we make it equal to something? We can make it equal to 11a. You could put any variable there you want, but you want to specify that a is an element of positive integers, right? Now, what does this do? We're saying we're plugging in k, yes, but we're also saying this plugging in for k is divisible by 11, because when we're solving this equation, we would be dividing a by 11, therefore dividing the left-hand side by 11. Therefore, we get an answer because it's divisible by 11. That's all you got to do. That's step number 2, easy. Now, step number 3, this is the annoying part, but if you see it, and it's the easiest problem in the world. And the more practice you have, the easier it will be to see it. So for n equals k plus 1. Now, my iPad is frozen. Still frozen. All right, we're back. So now for n equals k plus 1, we have 2 to the 4k plus 1 plus 3 plus 3 to the 3k plus 1 plus 1. Now, what is this really equal? 2 to the 4k plus 7 plus 3 to the 3k plus 4. Okay, so now what the heck do we do now? Well, remember, always look for a way to incorporate your step number 2. That's what you have to do. That's how you get to the right answer. Look for a way to incorporate your step number 2, because that is the stepping stone, as we said before. So what is our step number 2? 2 to the 4k plus 3 plus 3 to the k plus 1. Okay. Look at what we have. We have 2 to the 4k plus 7 and 3 to the 3k plus 4. What can we do, knowing our rules of exponents? When you multiply, they add. So what can we do? We could take out a 4 in the 2 to the 4k plus 7 and a 3 to the 3 to the k plus 4 to make it equal to the top, and I'll show you exactly what I mean right now. So if we take out a 2 to the 4th power, what can we then do? 2 to the 4th power is equal to, not 2 to the 4th power allows us to now substitute in 11a minus 3 to the 3k plus 1. Now, you're probably like, wait, hold on. What the heck did you just do? Or maybe you understand it perfectly, in which case, good for you. But what happens when you multiply? Exponents add. So 2 to the 4. And then if you're multiplying then by 2 to the 4k plus 3, what do you have? You have 2 to the 4k plus 7, which is what we have here. So we're actually, it's the same thing. We're just incorporating different values and getting to the right answer. So, also, we get the 11a minus 3k plus 1 because what did we say 4k plus 3 is equal to? 2 to the 4k plus 3. If we subtract 3 to the 3k plus 1, we have 2 to the 4k plus 3 is equal to 11a minus 3 to the 3k plus 1. That's all we're saying. And that's implied. You don't have to write out that math. The person that's grading your test will know that that's implied, that you're just plugging in, or that you just subtracted over. But yeah, that's just, I was just showing you the logic behind it. Okay, so I can delete this too. And now we also have 3 plus 3 to the 3 times what? Times 3 to the 3k plus 1. Okay, so we put in the 3 to the 3k plus 1. Oh, and just to explain why I'm not saying, 3 to the 3k plus 1 is 11a minus 2 to the 4k plus 3. That's because we're trying to get the same things, right? Remember what I said, you're trying to be smart with the moves you're making, right? You don't want to make moves and then realize, okay, I can't do anything with this. You want to think 1, 2, maybe even 3 steps ahead if you're that good. And so we see that if we plug in this, we could eventually have the same values to put together. Okay, so that's what we have now. So now if we multiply 3 to the third, so plus 3 to the third power is 27 times 3 to 3k plus 1. And then we could also multiply 2 to the fourth power is 16. And then we can multiply in, which would make 2 to the 16 times 11 is 176. 176 a minus 16 3 to the 3k plus 1. And that's called being smart with what you're doing. Now look how easy this is. We now have equals 176a plus 11 3 to the 3k plus 1. Now look at this. Ladies and gentlemen, we have made it, because what is this whole thing? What can we do? Take out an 11. So we have 11, 16a plus 3 to the 3k plus 1. Look at that. We can take out an 11 out of the whole thing. What does that mean? If we could take out an 11 out of the whole thing, that means the whole thing is divisible by 11. That's it. That's it. We can write our story now, which is, well, therefore, therefore divisible by 11, you could just say. And now we could write our story. I'm not going to write it, but what you could say is, on your paper, say as n equals 1 was proved true and n equals k was assumed true, then n equals k plus 1 was proved true. Therefore, 2 to the 4n plus 3 plus 3 to the 3n plus 3 is divisible by 11 for all n of elements of positive integers. You can do the n, the e thingy, and the z plus by POMI, or proof of mathematical induction. And that's it. That's mathematical induction. If you have any questions, feel free to ask a question in the comments. If you have any, if I made any mistakes or you want to see another type of mathematical induction problem, I tried to get a good little range, but if you want to see any others, or if you have any other questions or you have a request for kind of video, I'm only here to help. So just leave that there and have a great day, everybody. Hope this helped. Peace out.